Hello, we're continuing talking about percentage change, which is a part of exponential functions. This is part 3. And I do want everybody to remember you have access to the textbook, which is an important resource if you ever have questions or need to kind of double check ideas. You have access, online access to the textbook on your WebAssign homepage. Just look under resources. So don't forget that this is a valuable resource. And Little Women, Mark sisters are here. And whenever you see them, you know we're talking about exponential functions. Okay, we're going to look at some examples. Example 1, a certain home appreciates 5% per year. So appreciate just meaning that it goes up in value. 5% per year. In 1970, it was worth $20,000. Write a function to model home value as a function of years since 1970. When we see something going up by a constant percentage change, we know this is an exponential function. So this tells us that we're dealing with an exponential function. And this is going to be the value r. And remember that with an exponential function, the pattern for these functions is a times b to the x. A is an initial value and b is the change factor. R is closely related to the change factor, but it is not the change factor. So if r equals 0.05, and we know the formula, the change factor equals 1 plus r, then in this case, b equals 1 plus 0.05 or 1.05. Okay, so we probably have all the pieces we need. We now know what the change factor is. R is called the percentage change. In 1970, it was worth $20,000. This is important information because we are going to write a function that begins in 1970. This is our initial value. They say write a function to model home value as a function of years. So graphically, I think of the home value as a function of years. So as time goes on, what is the value of the home? And it starts at 20,000 and it's going to grow 5% per year. So in general, this model will look This function will look something like this. It's an exponential shape. All right, well, let's come up with the formula. I'm going to use, instead of y's and x's, I'm going to use v as the value, as a function of time, is a times b to the t. And the value of the home is the initial value, 20,000, times the change factor, which I found out was 1.05, raised to the t power, and that's it. That's the whole function. So we could find out for any year what the value of the home predicted by the model would be. We could find it out in 2020, which is 50 years after 1970, just by plugging in 50 for t. Okay, a car depreciates. This is example 2. A car depreciates at a rate of 15% per year. For a new car worth $40,000 at purchase time, what will it be worth in 10 years? Really similar setup. The only different thing is we're depreciating here. So a car depreciates at the rate of 15% per year. So here our r is, if it's depreciating, r is not 0.15, but it's going to be negative 0.15 is our r. Okay, and knowing that b equals 1 plus r always, the change factor equals 1 plus the percentage change, then in this case, b equals 1 plus negative 0.15. So b is going to be 0.85. And this holds to the pattern we would expect. Because things are depreciating, this is going to be an exponential function that gets smaller over time. And when you have a change factor less than 1, that is the case. So the car value, we'll call it CV. No, let's just call it V. Over time, it starts out at 40,000 up here, but it's depreciating. So it's getting smaller in an exponential way. Okay, so the car value is going to be some initial value times the change factor raised to the t power. So the value, the initial value of the car, 40,000 at purchase time. We found out that the change factor is 0.85 to the t. This is our function that's going to model what the car is worth. And they ask us to find out what it's going to be worth in 10 years. So V of 10 years equals 40,000 times 0.85 to the t power. So if you figure that out real quick, 0.85 to the 10th times 40, too many zeros, 40,000. Okay, so after 10 years, the car is only worth 7,875. We'll round to the nearest dollar. So car's value after 10 years. The last example in this video is a little bit more challenging, but that's good for us. I cannot remember what they're looking out at, but this is still Little Women, the March Sisters, so we're still talking about exponential functions. I know it's something important that they look at that window. Okay, a certain iceberg has shrunk 40% over the past 30 years. Find the annual decay factor. Predict what percentage of the iceberg remains after 52 years. The hard thing about this example is as we look over the whole problem, we're not really given an initial value anywhere. We're told how it's decaying, but we're never given an initial value, and we're asked to do two things: find the annual decay factor and then predict what percentage of the iceberg remains after 52 years. So I'm going to do my best. I'm just going to write down the information that I do know. I know that I want to use y equals ab to the x because of this right here, this percentage change. This tells me that we're dealing with an exponential function. If it's changing in a percentage, by a certain percentage every certain period of time. But that's not even really our annual percentage rate. It's over 30 years. So when I'm stuck like this, I will often go to I'm just going to draw a table and write out what I know. And this function is going to be over time, and we'll call this A, the amount of the iceberg that remains. So, no, let's call it mass, because we have another A already. Okay, so the mass of the iceberg over time is going to be some initial value times the change factor raised to the t, which is years. Okay, so my input is t and my output is mass. I know that I don't know the initial value. So for right now, I'm just going to call it M1. Because I do know that 30 years later, it's shrunk by 40%. So the mass that remains after 30 years is 60% of my initial value. So I still have 60% of what I started with. And I'm hoping that this is enough information to answer the questions that they give me. But before I go any further, I want to give you another extra credit opportunity. If you've been listening this far for 3 extra credit homework points, if you do number 16 on page 336 in the textbook, it's a relatively easy problem, or more straightforward problem, I'll say. If you do number 16 on page 336, then you can have 3 extra credit homework problems. Okay, back to our problem. I do also remember that I have this formula where the change factor is a y value over another y value raised to the 1 over x2 minus x1. So I have these two values, and I'm going to put them in here and try to come up with some sort of change factor. Okay, so in my case, my second y value is this guy, 0.60 of the initial mass. And this is my first y value, m1. Things are looking pretty good because I see that these are going to cancel out. That's handy. And then it's raised to the 1 over my second input value, which is 30, minus my first input value, which is 0. Okay, things are looking really nice because these cancel, and now I just have 0.60 raised to the 1 over 30. And that's just a plain old number. We can figure that out. So 0.6 raised to the 1 divided by 30. And remember to use your parentheses. Okay, so this ends up being 0.9831. And this is our B. We just found the change factor. Okay. They don't ask for the change factor, they ask for the annual decay factor. In other words, they want to know what R is. What's the annual decay factor? Well, then I remember that B equals 1 plus R. So I have my 0.9831 equals 1 plus R. And I can just solve for R. Subtract 1, subtract 1. So R equals negative 0.016. We'll say 8. Nope. Yeah, we'll say 88. This is the annual decay factor. And if we wrote this as a percentage, it means 1.688% of the iceberg shrinks. Well, goes away, melts every year. Okay, we have done the first thing that they asked us to do. Predict what percentage of the iceberg remains after 52 years. All right, I do have B. I still don't really know my initial value, but we'll do the best we can. We have this formula so far. The mass of the iceberg over time is the initial mass times our change factor, 0.9831 raised to the t power. Okay. After 52 years, I have this times the change factor raised to the 52nd power. 0.9831 to the 52nd is M1 times 0.4122. Okay, another way of writing this is 0.4122 times M1. And really this means that after 52 years, I have about 41.22% of the original mass, or M1, left. So I've answered their second question. Predict what percentage of the iceberg remains after 52 years, 41.22%. All right.